Okay guys, here we are again. I haven't gotten any better at this, so please bear with me as we get through this lesson today. So here's your warm-up. Try to do it on your own, and I'm going to do it up here. So yeah. Okay, so selecting a 2. Well, how many 2s are in the deck? Ooh, look at that. There are 4 2s out of 52. So the probability of selecting a 2 is 4 out of 52, which is 1 out of 13. Okey-doke. And what about selecting a face card? Well, what is a face card? Well, like down here, it's a card with a face on it. And Jack, Queens, and Kings all have faces on them. So that would make this 12 out of 52. And we're going to divide top and bottom by 4. We're going to end up with 3 out of 13. Now we're drawing 2 cards and finding each probability. What's the probability of selecting 2 kings when the first card is replaced? So the key word here is being replaced. So once I take a king out of the deck, I am going to put it back in for the second draw. So then my probability is 4 out of 52 times 4 out of 52. Since I replaced that first king, that's going to be 1 over 13 times 1 over 13, which is 1 out of 169. Okay? Last of all, I have selecting 2 hearts when the first card is not replaced. Now remember, there are 4 suits in the deck, 13 cards to a suit, so I have 13 out of 52 chance of selecting 1 heart. Okay? Now I'm not replacing that card. So I now have 51 cards left. I've already used 1 heart, which means I have 12 left. So now, instead of doing all the multiplying here and using big numbers, we're going to simplify. If we divide top and bottom by 3, I get 4 over 17. Now I'm going to divide the top and bottom by 4. I get 1 over 13. My 13's cancel. I get a 1 out of 17 chance. So there you have it. Okay, so our objectives today are to find the probability of mutually exclusive events and to find the probability of inclusive events. Your language objective, describe the difference between mutually exclusive and inclusive events. Vocabulary event. Vocabulary. A simple event, let's see, where's my cursor? Simple event is one thing happening, so that would be like one roll of the die. Compound event is what we've been doing with the 2 rolls of the die. So the event would be, okay, on 2 rolls of the die. Mutually exclusive events are things that cannot happen at the same time. So one example would be rolling a 5 and rolling a 3 on 1 roll of the die. It's virtually impossible because you can either have the 3 or the 5, but you cannot have both. An inclusive event would be having more than one event happen, and they could happen at the same time. So for example, if you were doing 2 things, you could roll a die and flip a coin. So if the event was rolling a 1 and getting a head on a coin, that would be possible because they're 2 separate things that you can do at the same time. So a simple event is an event that describes a single event. Ooh, that's ugly. A compound event is an event made up of 1 or more events. I'm sorry, 2 or more events. Mutually exclusive events are events that cannot both occur at the same time or the same trial of an experiment. So if you look over here, mutually exclusive event, either you have event A or event B. There's no overlap whatsoever. Can you think of an example of a mutually exclusive event? So you might say flipping heads and or flipping tails on a coin. So you can have heads, you can have tails, but you can't have both. Okay? Those are mutually exclusive events. So, in words, the probability of two mutually exclusive events A or B occurring is the sum of their individual probabilities. So for two mutually exclusive events A and B, the probability of A union B is going to be the probability of A plus the probability of B. So when a number cube is rolled, what's the probability of getting less than 3? Well, the numbers on the number cube that are less than 3 are 1 or 2. Probability of getting 1 is 1 over 6. Probability of getting 2 is 1 over 6. We combine that to get 2 over 6, or 1/3. Okie doke. Recall, you see what this symbol right here means? The union symbol? Let's see, where's my cursor? That means or when we're talking math, okay? So a group of students is donating blood during a blood drive. A student has a 9/20ths probability of having type O blood and a 2/5 probability of having type A blood. Are the events type O and type A blood mutually exclusive? Well, what do you think? Can you have more than one type of blood? No, so they are mutually exclusive. A person can only have one type of blood. So you can have type O or you could have type A, but you cannot have both. So what is the probability a student has type O or type A? So what we're doing here is we're taking everything in the group, we're putting it into one big group where you have a type O, your type A, and so you're just adding them together. So we're taking the group of 9/20ths, we're adding it to the group of 2/5, and then we have to get a common denominator, so we multiply top and bottom by 4. And we get 9/20ths plus 8/20ths for a total of 17 over 20. And there's your probability. So whenever you see an OR, guys, what you want to do is add your probabilities if you're talking mutually exclusive events. So here's a problem that you guys can try. I'm going to do it up here silently while you work on it, and then see what you think. What's the probability that a student voted for Klein or Vila? So I hope you got 75%. Every student gets one vote, so they're mutually exclusive. 20% voted for Klein, 55% for Vila, so together 75%. Inclusive events are events that have two or more, or you could say more than one, either way, two or more than one, outcomes in common. When you roll a number cube, are the outcomes rolling an even number and rolling a prime number mutually exclusive? Why or why not? Let's look. If we roll an even number, we're either going to have 2, 4, or 6. So 3 numbers possible. If I roll a prime number, I'm going to have 2, 3, or 5. Now let's see what happens if we add those two probabilities together. I have the probability of even plus the probability of prime. Now you can see that the probability of being even is 3 out of 6. I'm going to add that to the probability of 3 out of 6. That gives us 6 out of 6, which is 1. But what happened here? Look here, I counted the 2 twice. So I have to subtract one of the 2's that I counted. you're not going to get a probability of 1 because we don't even have the option of rolling a 1 here. So what I need to do is up here subtract the 2 that I counted twice. So that's going to be 1/6, and I'm going to end up with 5 out of 6 times I'm going to have an even or a prime number. Okay? So I can roll an even number 3 ways. I can roll a prime number 3 ways. I can roll an even number or a prime number 5 ways. Okay? So the probability of 2 inclusive events, A or B, occurring is the sum of their individual probabilities minus, subtract, the probability of both occurring. For 2 inclusive events, A and B, the probability of A union B is the probability of A plus the probability of B minus the intersection, the probability of A intersection B. Okay? So for example, when you roll a number cube, the probability of even number or prime is the probability of even, which was 3 out of 6, the probability of prime, 3 out of 6 minus the repeat, even and prime. So you're going to get 3 out of 6 plus 3 out of 6 minus 1 out of 6, which equals 5 out of 6. Remember, the upside down U means and. That means the intersection, something that is two things that are occurring. So let's find the probability of rolling a 4 or an even number on a number cube. Well, the probability of rolling a 4 is going to be, let's erase that. No, I can't erase it. Okay. So I have the probability of the 4 plus the probability of even minus the probability of 4 and even. Okay? So the probability of rolling the 4 is 1 out of 6. The probability of rolling an even number, either 2, 4, or 6, is 3 out of 6. Now, I counted the 4 twice. I counted the 4 here and I counted the 4 here. So I have to subtract the probability of being 4 and even. Well, 4 is even. So I have to subtract 1 out of 6. My answer is going to be 3 out of 6, which equals 1/2. Okay? How about this one? Rolling an odd number or a number greater than 2. Well, the odd numbers on the die are 1, 3, and 5. So I'm going to have the probability of odd plus a number greater than 2. Probability greater than 2 minus the probability of odd and, ooh, that doesn't look like an and. Greater than 2. Okay? So, like I said, probability of odd is 1, 3, or 5. That's 3 out of 6. Probability of being greater than 2. Well, what numbers are greater than 2? You have 3, 4, 5, and 6. So 4 out of 6 minus the probability of odd and greater than 2. So odd numbers are 3 and 5, and they're greater than 2, so minus 2 out of 6. That's going to give us 7 minus 2, which is 5 out of 6. Okay, you guys try these two. I'm going to do them silently up here while you do them there. Okay, so you should have gotten 4 out of 13 and 8 out of 13. Okay? Okay, we're going to use a Venn diagram for this one. Of 1560 students surveyed, 840 were seniors and 630 read a daily paper. The rest of the students were juniors. Only 215 of the paper readers were juniors. What is the probability that a student was a senior or read a daily paper? Here's my 67.2%. So, there you have it, 67.2%. Okay, why don't you guys do the next one? The Venn diagram's already there for you. I'm going to do it up here while you do it at your desks, okay? Okay, the complement of an event with probability p, all outcomes that are not in the event, has a probability of 1 minus p. You can use the complement to find the probability of a compound event. Each of 6 students randomly chooses a butterfly from a list of 8 types. What is the probability that at least 2 students choose the same butterfly? Well, the probability that at least 2 students choose the same is 1 minus the probability that they all choose different. So the probability that all the students choose different butterflies is going to be the number of ways students can choose 6 butterflies. Or, I'm sorry, the number of ways 8 butterflies are chosen by 6 students. Okay? So 8 ways, or 8 butterflies to be chosen by 6 students. Now, you might be asking, why is this a permutation? Because they're choosing the same butterfly, one butterfly. So yes, order matters here. So how many different ways can 8 butterflies be chosen? Well, one student could choose 8 butterflies. The second student could also choose 8 butterflies, as well as the third, fourth, fifth, and sixth. So 8 butterflies can be chosen in 6 ways. So I'm going to stick that into my calculator. And I'm going to get 20160 over 8 to the 6th, which is 262,144. Which is approximately 7.7%. So this is the probability that they all choose different butterflies. So the probability that at least 2 students choose the same, or at least one butterfly the same, is going to be 1 minus this, which is going to be 92.3% chance of choosing the same butterfly. Okay? So basically, find the permutations or numbers of ways that they could choose different, subtract it from 1. Okay? Okay, that brings us to our language objective, which is this. You guys can just fill it in, and your homework is at the end there. So have a great day. I'll see you next week. Bye.